All right, we continue looking at questions from the back of the chapter in the structure of atoms and periodic trends. Where's my pen? Here we go. Rank the following in order of increasing ionization energy. So remember that ionization energy is the following, where you take atom in the gaseous state and you add ionization energy, so it's a reactant. So this is endothermic, and you end up taking an electron from the atom, so it ends up having a positive sign, and the electron is pulled away, presumably to infinity. Okay, another way to look at it is that you have some atom, we'll call it X, and you take this electron and you remove it. So the amount of energy you have to put into this system to remove the electron away from that nucleus is the ionization energy. So we're going to be looking at chlorine, calcium 2+, and chloride ion. So what we want to do here is we want to try to examine which electron is being taken from each of these so that we can compare and see which one is going to be easier and which one's harder. So chlorine, if we start here at neon, it's going to have an electron configuration of neon 3s2 3p5. For chloride ion, it will be neon 3s2 3p6. So here, this is 3p6 because it's the same as chlorine, but it has one extra electron. And I want you to recall that for anions, the electron configuration is pretty much the same as the noble gas in that same period. Now, calcium 2+ is going to be neon 3s2 3p6, which is the same as it is for chloride ion. So here, if we take a look, in each case, we're removing a 3p electron. Okay, so considering that, in each case we're removing a 3p electron, we then need to consider what else might affect the energy required to remove these. And here, what we're going to do is we're going to take a look at the number of protons for each of these. Chlorine has 17 protons, so I'm going to put atomic number, Z. Calcium has 20, and of course the chloride ion has 17. So let's think about the size of these things when we consider what's going to be the easiest electron to take. So when we look at the size of each of these, so here is the nucleus for each of these. And we're looking at the outermost ring here. If you take, actually, I'm going to redraw this. I'm going to cross all these out. And we're going to do this versus this versus this. So here, if we take this to infinity, or this to infinity, or this to infinity, this arrow kind of represents the amount of energy it takes to remove the electron. So since this arrow is longer, it's going to take more energy. Since this arrow is the shortest, it's going to take the least energy. So based on what we have here, that we're looking at the third shell for each of these, and in fact the same subshell, and we have the different number of protons here, which one is going to be the smallest and which one's the largest? Now I would argue that since they all pretty much have the same number of electrons, we're going to have to say that the calcium is going to be the smallest because it has 20 protons pulling those electrons in. So I'm going to say calcium plus 2 is going to be the smallest. Now, what about chlorine versus chloride? We're supposed to know that when you have the same number of protons, the large one is going to be the one with more electrons. So chlorine will be the next in line, and chloride will be the biggest. So if we're taking an electron off into infinity, we've got to understand that the highest ionization energy is this on the left, the lowest is on the right, and the midlist, as it were, is in the middle. So we want to do this in order of increasing ionization energy. So we've got to go with chloride is smaller than chlorine is smaller than calcium 2 plus. And that would be our answer right there. Okay, good. Now we're going to move on to the next one. All righty. Let's look at number 54. Answer the following questions about elements with electron configurations shown here. Is element A metal, metalloid, or non-metal? Now, the way I would approach this is I would just look at that 4s2. We can do this one of two ways, and one way is to look here at the periodic table, and we see that 1s, 2s, 3s, 4s. 4s2 ends right here with calcium, so I think it's calcium, which means it's a metal. Basically, if it ends with an S, you're probably going to say it's a metal. But another way to do this, of course, is to count the electrons, and then that's the number of protons it has, and find out exactly where this is also. So argon has 18 electrons, plus 2 more puts it at 20, which means it is indeed calcium. So we're going to have to say A is definitely a metal. And the reason why is it has 20 electrons, which means it has 20 protons, which means it's calcium, which means it's a metal. Okay, how about B? Is element B a metal, metalloid, or non-metal? Now, do you see how this is a 3D10, 4s2, 4p5? So the 4p5 puts it right here, 2D, 3D, 4D, 4p5 puts it at bromine, I believe. So bromine has 35 protons. So for B, we can do the same thing. We're going to say it's a non-metal. And the reason is that it has, for argon, it's got 18 electrons, plus 10, plus 2, plus 5 electrons. And when we add that all up together, we get 18, 28, 30, 35 electrons, which means it's got 35 protons, which means it is bromine, which is a nonmetal. Which element is expected to have the larger ionization energy? So we now know that we have calcium here, and we've got bromine over here. They're both in the fourth period. Okay, so what do we know about ionization energy? We know that ionization energy has a lot to do with size, if you were. And if this is a calcium, then this is what we'd expect for a bromine, because in the same row, same period, we expect the size to get smaller as you go farther to the right. And that's because you have more protons pulling in that outer shell. And so these would be smaller because this has 35 protons, whereas this only has 20. So here, if you wanted to remove an electron, so when we're removing the electron to infinity here, and this is the ionization energy of each, the ionization energy of calcium, the ionization energy of bromine, you can see that arrow is quite a bit longer, so that's going to have the greatest ionization energy. So for letter C, you expect bromine to have the greater ionization energy because you're taking a 4-shell electron from a larger nucleus. Okay, DS, which element has the smaller atomic radius? Well, we've already answered that. Bromine has the smaller radius. And that's because it has more protons for a outermost occupied shell equal to 4. And here, bromine has the larger ionization energy because it has more protons keeping the electrons on the atom. Okay, so that's the answer to number 54. Okay, 56. Place the following ions in order of decreasing size. So we want to go from large size to small size. Now, normally when we talk about these, we talk about them in terms of the radius or diameter at worst. Now, naturally, a smaller radius is going to be a smaller size. Okay, so we're looking at K plus, we're looking at chloride ion, we're looking at sulfide ion, and we're looking at calcium ion. Now, if we look at the electron configurations of these, if we look at chloride, it's going to be the same as argon, so the noble gas in that period. So I'm going to put neon, because when we use the noble gas / SPDF notation, you always start with the noble gas preceding. So if this is going to look like argon, we're going to say neon 3s2 3p6. Now, sulfur is in the same period as chloride, so it is also going to have the same electron configuration. Now, calcium ion will also have the same electron configuration. Now, what about potassium ion? It also has the same electron configuration. So what that means here is that when you look at the number of electrons on each of these, they all have the same number of electrons as argon. So they all have 18 electrons. So you might think, okay, so they're all the same size because they all have the same number of electrons. But there is a difference between each of these. Let's look at the number of protons. So I'm going to put Z here, 19, 20 down here for calcium, 17 for chlorine, and 16 for sulfur. So what is going to make the radius smaller and what's going to make it larger? Well, what's going to make it smaller is more protons in the nucleus. So this is going to be the smallest. And this is going to be the next smallest. And this one with the fewest number of protons will be the largest. And this will be the next largest. Now we're supposed to put them in order of decreasing size. So that means we want to start large and go small. So we're going to have to say that the sulfide is the largest. The chloride is the next largest. Then the potassium ion is the next largest. Then the calcium ion is the smallest. And remember, the symbol we want to use is this, because if you think about this, the smaller one is always next to the ends that meet, and the larger one is next to the ends that are open, because the open ends are farther apart than the closed ends. So there's your answer. Okay, great. 62, refer to the book. That means we skip that one, and we go to 68. Which ions in the following list are not likely to be found in chemical compounds? Explain briefly. So we know K2 is not, and that's because K is in group 1A, and forms +1 cations. Okay, so that's what we learned previously in previous chapters, but we are now at the point where we should be able to explain why it doesn't form a +2 and why it only forms a +1. So let's take a look at potassium, which is 1s. Well, actually, I'm going to go ahead and start at argon. Actually, I'm going to write out the whole electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. So when we look at this potassium ion, so here's potassium, not the ion, but the atom. We've got 2 electrons here in the first shell. In the second shell, we've got 8 electrons. In the third shell, we've got 8 electrons. And in the fourth shell, we've got 1 electron. So why does K2 plus not happen? Well, the answer is because it's a lot easier to pull a fourth shell electron off of an atom than it is a third shell electron. So here, we would say to form K2 plus, we would have to take a third shell electron off in addition to the fourth shell, and it just costs too much energy. So it costs too much. We could also add this. To make K2 plus, we would have to remove an electron from a 1s2, 2s2, 2p6, 3s2, 3p6 configuration, which is known to be stable, because it's the same electron configuration as a noble gas. And what do we know about noble gases? They're stable. Okay, so that's a pretty brief explanation. Okay, so we're not likely to find a K2 plus. So now we look at cesium plus 1. And the answer is yes. Why yes? Well, because we only have to remove a 6s electron, and then you get a configuration like xenon, a stable noble gas. Okay, what about aluminum plus 4? And the answer is no. And the reason for an aluminum plus 4 is that we'd have to take away an electron from a stable noble gas configuration for like aluminum plus 3, and so forth and so on. So this is going to be the same explanation as K2 plus, similar explanation. F2 minus, no, but this one, we have to explain why it's not going to get an extra electron. Well, F minus is 1s2, 2s2, 2p6. Here, we would have to add an electron to a F minus ion, which seems like a bad idea, right? Adding a negative to a negative. Okay, and then the last one here is an Se2 minus. So Se2 minus, we'd say yes. And that's because the electron configuration looks like a noble gas. which is stable. So you don't want to write, yeah, because it's going to look like a noble gas. You want to say a little bit more than that. You want to say, yeah, it's going to look like a noble gas. And we know that once you get a noble gas configuration, they tend to be stable. That's why they're called noble gases. They're unreactive and they're rare. Okay, so that's number 68. All right, so 70 was clearly too long of one to do. So we're going to look at 72. The bond lengths in chlorine, bromine, and iodine are 200, 228, and 266 picometers, respectively. Knowing that the tin radius is 141 picometers, estimate the bond distances in tin and chlorine, tin and bromine, and tin and iodine. Okay, so the way we're going to do this is we're going to draw each of these. So here is chlorine. We have two chlorines, and this is considered to be the bond distance right here. So that's 200 picometers. Now for bromine, it's 228. So we're going to draw atoms that are a little bit bigger here. So this is a bromine and this is a bromine. And here, this distance here is going to be about 228 picometers. And then, of course, for iodine, we have 266, so we're going to draw even larger atoms. And here we have 266 picometers. So those are the bond lengths. The bond lengths are defined as being the distance between the two nuclei. Okay, so what do we want to take away from this? We want to take away from this that we can get the radius from the bond length. The bond length is clearly one radius plus another. So the radius here is going to be 100 picometers. The radius here is going to be 114 picometers. And the radius here is going to be 133 picometers. Okay, so we know that the tin radius is 141. So basically we're going to take this chlorine, and I've drawn it too large, so naturally I have to cross that off. I'm going to draw my chlorine similar in size to that. And we know that from here to here is 100 picometers. And now we're going to put our tin here. So here's our tin. And we know that this distance is 141. So we expect the bond length to be about, let's see, 241 picometers. Same with bromine and tin. For bromine, I'm going to put my bromine here. And we know that this distance here is 114. So when I put my tin here, this distance is 141. So when we add the two together, we get 256 picometers. And then lastly, we have our iodine, where this distance here is 133. And then we have our tin, where this distance here is 141. So when we add the two together, we get 174 picometers. So this is what we expect based on the given information. Now they say it's 233, 250, and 270. Oh, and this should be 274, not 270, not 174, because 1 plus 1 is 2, right? All right, so what would we say here? We'd say, well, it's not bad. It came out to be pretty good. So it's pretty close. I mean, we could even calculate a percent error, right? What is the percent error for this one? Well, it's going to be the difference, 241 minus 233 over 233 picometers. And so when we calculate that, and times 100%, let's see, where's my calculator? We're going to get a difference there of what? 8 over 233, which comes out to be less than a 4% difference, I think. So 8 divided by 233, and then times 100%. And we get this is a 3% difference. And here, the difference is going to be 6 out of 250 times 100. And so this ends up being a 2% difference. And here, this is 4 out of 270, and then times 100%. And this ends up being a 1% difference. I'm rounding off to 1 zig fig. So, you know, when we take a look at these numbers here and we look at the error, there's a very small amount of error. So I'd say that what we predicted based on each of these individual ones turned out to be pretty darn good. Okay. So we're done with number 72. And now we'll look at 74. What is the trend of ionization energy when proceeding down a group in the periodic table? Rationalize the trend. So remember, a group is a column of elements. So that might be lithium, sodium, potassium, etc. So what is the trend when we go down a group? So when we go down this group, what happens to the ionization energy? And it turns out that this arrow actually matches it pretty good. The ionization energy becomes smaller. So rationalize this trend. Well, for lithium, it's 1s2, 2s1. So you remove a 2s electron. Sodium is 1s2, 2s2, 2p6, 3s1. So you remove a 3s electron. Sodium is going to be 1s2, or excuse me, potassium, 2s2, 2p6, 3s2, 3p6, 4s1. So you remove a 4s electron. So the deal is that it's harder to remove an electron from a shell that's closer to the nucleus. So this one's going to be the hardest, second hardest, and the least hardest. Or if we were to say, this would be the easiest, this would be the middlest, and excuse me, the other way around, this would be the hardest, the middlest, and the easiest. And the reason this is the easiest is because you're removing an electron that's farther away from the nucleus. Okay. Let's see how many more of these we have to do. 3, 4, 5. I think we're going to do just one more of these. So this one is supposed to take you to the next level of thinking here. Which of the following elements has the greatest difference between its first and second ionization energies? So we're going to look at carbon, which is 1s2, 2s2, 2p6. We're going to be looking at lithium, which is 1s2 and 2s1. We're going to look at nitrogen, which is 1s2, 2s2, 2p, and this is supposed to be 2p2 up here for carbon. And this is 2p3. And then we're going to look at beryllium, which is 1s2, 2s2. Okay, so what electrons are we taking here for the first electron and the second electron? So here, this is the list of electrons being taken. Well, the first one is a 2p electron, and the second one is a 2p electron. So it doesn't seem like there should be a big difference between those two. For lithium, the first is a 2s electron, then a 1s electron. Those seem like they should be very different because you're looking at the first shell versus the second shell. How about a nitrogen? You're looking at a 2p versus a 2p. And for beryllium, you're looking at a 2s versus a 2s. So I've got to say this is going to be the greatest difference because we're removing electrons from different shells. Okay, so that's that one. Thank you for listening.